When you are asked to describe the difference between the so-called Doppler redshift and the cosmological redshift of light from distant galaxies, you've got to distinguish between two processes, one of which is the idea that things can move through space. So, for example, I can get the pencil and I can move it from left to right, and I say I'm going through space. But the other thing which we think is happening is, and it's something that nobody really understands, is that space itself seems to be expanding. And, as it were, carries things with it. And it's a very difficult thing to try and understand, but the way often it's simulated as being is to take a balloon and blow the balloon up and paint a little dot on the surface of the balloon, some dots, and watch them move apart. And that is likened to space expanding. So the idea is you can move through space. So ambulances, for example, move through space on their way to their emergencies, and the sound that their sirens give out, there's a change in wavelength, there's a change in frequency. That's the so-called Doppler shift. And then you've got this other phenomenon of space expanding, carrying things with it, as it were, and causing things to move further and further apart. So the answer I've got here is that the so-called Doppler redshift, now don't forget the galaxies that are near us, they do show redshifts. In fact, they show blue shifts sometimes as well, and they are said to be due to the galaxies moving through space. It's the change in wavelength anyway and frequency which occurs due to the relative motion of the source and the observer through space. Now the question does say you've got to talk about the source of the light and the observation of the light as well. So it's going through space. Now I noticed that the mark scheme did not include that little phrase through space, but it's crucial to the idea. Whereas the cosmological redshift is due to space itself expanding, and that means it's expanding between the source and the observer. So the idea is if I got one pencil here and I got another pencil there, and I just left them there, after a while I'd notice that the space between them would have got bigger, simply because space is expanding. Now you'll find that if you were going to leave two pencils like that and come back the following day looking for an increase in space, you would see virtually nothing at all. It's an absolutely tiny increase, but nevertheless we think it's occurring. When it comes to the notes which describe that, here's one little diagram that's done. This is a diagram representing time, and here's a photograph, as it were, of some light, and you can see that the waves are all bunched up, and then as time goes on, you take another photograph and you'll find because the space has expanded, the crests have got further apart. This, of course, is going to explain the cosmic microwave background radiation. The idea is you start off with some infrared, and as time goes on, space expands and the light stretches, as it were, the wavelength gets bigger. And here it is a bit later on, expanded even more. And the calculations they did suggested that the infrared, which was formed in the early part of the universe, should now have stretched into microwaves. And they have since been discovered. When you try and simulate the process with a balloon blowing up, this is often a diagram which is done. There are some dots that you can paint onto a balloon, a distance r apart. And then because the balloon expands, space expands a bit later on, they're a bit further apart, as you can see. And everything moves away from everything. If you lived on that galaxy and you looked at that one, you'll find it's moved away from you. If you lived on that galaxy and you looked at that one, you'd notice it's moved away from you. There's you, there it is now. And it doesn't matter which galaxy you live on. Even if you live on that one, you will see that one moving away from you, you'll see that one moving away from you, and so on. In actual fact, it turns out, and it's quite easy to see, that if you live on that one, and you watch that one moving away from you, and you measure its speed, you will see that one moving away from you twice as fast, because that one also moves away from that one. And if that one moves away from that one, it's got to move away from that one even faster. Anyway, that's the idea behind the expanding universe. Going back to the question, it then talks about the spectrum of light from a distant galaxy, and it contains a spectral line of 398.6 nanometers. Now that is too long. It's longer than it should be. When you measure the same line in the laboratory, i.e. from a stationary source, it's got a wavelength of 393.3 nanometers. So clearly that's been stretched. And what you've got to do is calculate the so-called recession speed of the galaxy and give your answer to 3 significant figures. Now, the cosmological redshift, denoted with the symbol Z, is defined as being the change in wavelength, which we can easily calculate, divided by the wavelength it ought to be, and that's sometimes known as the fractional change in wavelength. And when you do the analysis, the mathematical analysis, it turns out that it's equal to the speed of recession divided by the speed of light. So all you've got to do is make sure you know that formula, and then put your numbers in. Nanos, of course, are 10 to the minus 9s, and you put your numbers in, and the velocity comes out fairly easily, 4.04 times 10 to the 6 meters per second. These are the spectra that they've been talking about. At rest, this is the spectrum of, say, hydrogen, and then a redshift would have a spectral line moved over to the right towards the red end, i.e. The wavelength has got bigger. There's the formula for the cosmological redshift parameter, change in wavelength, divided by the wavelength that you measure in a lab, and it's the ratio of V to C. Before we get into the next one, might be worth having a little look at the graph that was drawn of the velocity of these distant galaxies against how far away they were. And you can see that the points that have been plotted here, there's a lot of scatter on it. But nevertheless, they were able to very roughly show that the velocity and the distance were directly proportional. You can see that the accuracy, there's a bit of quite a bit of leeway there. Anyway, it says use Hubble's law to estimate the distance to this particular galaxy. Well, if you accept that the velocity of recession is directly proportional to how far away the galaxy is, then there's Hubble's constant, which is on the datasheet, and you can work out how far away the galaxy is. And it's a big distance, 1.68 times 10 to the 24. And then why is this just an estimate? Well, you can see from the graph that we looked at that there's a huge amount of scatter on the points on the graph. So that value of the Hubble constant, which of course is the gradient of the graph, that is very much an estimate.